I will turn it over to Vesna Stoyanowska, who will introduce our third speaker.
Thank you, Dan. Yeah, so our third and last speaker for today is Inbar Klang, who will talk to us about some isovariant fixed point theory. So I guess not so motivic anymore. Inbar?
Yeah, thanks. Thanks. It's really great to be here. Whatever be means and here means right now. So my talk is going to be extremely non-motivic. So I hope that'll be okay with this the theme of this conference. So thank you so much to the organizers for putting all of this together. It's been a really great workshop, and I know that it definitely must be really challenging to organize such a thing remotely, and I think it's been really good so far. So thank you to everyone. Okay, so I'll talk about isovariant fixed point theory, and this is work in progress with Sarah Yackel. And I would like to especially thank Carrie Malkovich and Kate Ponto, who've been extremely generous with their time and their energy in talking to us about isovariant things and about homotopical fixed point theory. And I'll be looking at the chat, or at least trying to look at the chat as much as I can, and the participant list thing. So if you have a question, then hopefully I'll be able to see it and respond to it. Okay, so I'll start by defining what isovariant means. So maybe let's start by let X and Y be G spaces. And for us, G is going to be a finite group. So here's the definition. For this one. Okay, so a map F from X to Y is called isovariant if it's equivariant and it preserves the isotropy groups. So isotropy of a point F of X is equal to the isotropy of X for all X and X. So just to set notation, by G sub X, I mean all of the elements of G that fix the point X. All right. So just a note about this definition. That for F that's only equivariant, we only know that Gx is contained in Gf of X. So just an equivariant map might increase the isotropic groups. Okay, so here are some examples of isovariant maps. So maybe one thing that's good to note is that any injective equivariant map is isovariant. Yeah, so every injective equivariant map is isovariant, but there are plenty of isovariant maps that are not injective. So for example, if you're including a point with a trivial action into maybe a disk with flip action, then that's going to be isovariant. So here's maybe a picture for this. Here we have a point, and we're including this into, here's a disk. Its middle is also fixed. Everything that's not the middle is free. And maybe that point goes to somewhere on the equator here. So the orange here denotes things that are, maybe let's say, isotropy G, in this case C2. And the blue is isotropy, just the trivial group. And here the group is acting by flipping. So this is isovariant, but the map in the opposite direction is not. So if you're taking this disk with a flip action and you're mapping it down to a point with trivial action, that's an equivariant map. Anything that you map down to just a point with trivial action is equivariant. This is a terminal object, but this map is not isovariant. So one thing that's kind of been weird working with the category of isovariant spaces is that there's no terminal object, and that's kind of a weird thing, but there's ways to get around it. All right, so maybe I'll move on to a more general set of examples. So let's say that we have two maps, F and G, from a space X to itself, and that they are homeomorphisms. So let F and G be homeomorphisms. So if F and G are isotopic, then F to the n and G to the n, so both of these from the n-fold product of X to itself, are isovariantly homotopic. So here, the action that we're taking on X to the n is, well, the n-fold symmetric group acts on the n-fold product by permuting the factors. All right, so this is suggesting that maybe studying maps up to isovariant homotopy could give some kind of new perspective on isotopy invariance for embeddings or for homeomorphisms or for things like that. So that's one of the hopes. So another thing that sort of related to these kinds of geometric questions is that, studying a G manifold, let's call it M, isovariantly is in a way the same as studying the stratification of the space M mod G by isotropy. So isovariant stuff has a lot to do with stratifications. Isovariant spaces are a particular kind of stratified space. And if you're asking questions about stratified spaces, then maybe a place to start or a place that might provide indications about answers to these questions might be isovariant spaces. All right. So that's kind of some examples slash different questions that are related to this stuff. Maybe I'll also say that isovariant maps arise in surgery theory. So like a lot of the times you will have some isovariant map occurring or an equivariant map that you'll want to know when it's homotopic to an isovariant map. So definitely shows up there too. Okay. So here's kind of the question that Sarah and I are working on. So if we have an isovariant map, f from x to x, when can we remove its fixed points? So when can we find, let's call it f1 from x to x, which is isovariantly homotopic to f. Such that f1 has no fixed points. So no fixed points means f1 of x is not equal to x for all the points in the space. So that's the question that we're studying. And so isovariantly, I don't think this has really been studied yet, but there's definitely been a lot of work in fixed point theory. And in particular, there has been a lot of work in fixed point theory that uses homotopic theory. So let me talk a little bit about homotopical fixed point theory and sort of our perspective on it and how we're hoping to use that for isovariant fixed point theory. All right. So homotopical fixed point theory. All right, if someone is having some kind of clicking in the background, if you can turn off your microphone, that'd be great. Okay. So homotopical fixed point theory. So let me start with the way this goes non-equivariantly. So for just a map between manifolds, when can you remove its fixed points? So here's the theorem. And in the formulation that I'm discussing, this is due to Klang and Williams. So we're taking M be a compact manifold, and F from M to itself is a map. Okay. So what they did is they produced an invariant which we'll call chi of f. This is some kind of characteristic thing of f in the zeroth stable homotopy group of the twisted free loop space of M. So I'll soon define what that is. Such that the following things happen. So first, if F is homotopic to a map without fixed points, then this chi of F is equal to 0. Okay. The second is sort of a converse to that. So this says that if chi of F is equal to 0, and the dimension of this manifold is at least 3, then F is homotopic to a map without fixed points. so that's kind of a converse and a pretty strong converse. So it's essentially saying if your manifold is at least three-dimensional, then this is a complete invariant. This invariant tells you exactly whether you can remove the fixed points of F. So that's a pretty good theorem, and that's kind of the theorem that we're looking for in the isovariant context as well. So what is going to provide for us, under some reasonable conditions, a complete invariant for removing the fixed points of a map. All right. I'll pause for a few seconds in case there are questions up to this point.
Does this kind of imply that homotopy equivalent manifolds kind of have the same interaction with fixed points for their functions?
Yeah, I guess. So like in general, fixed points of maps have a lot to do with, well, so anyway, okay, let's see. So this is up to homotopy anyway, right? So this is just saying, can we homotope it to a map without fixed points? And so I guess it makes sense that if manifolds are homotopy equivalent, then if you can homotope a map on one of them to not have fixed points, then you can homotope a map with the other.
Okay, so the twisted loop space will be
yeah.
for homotopy equivalent manifolds?
Yeah, oh yeah, so thanks. Let me define what this twisted free loop space is. So, so these are paths in M such that their endpoints are F of their starting point. So these are paths that start at some X and end at F of X. So if you take F to be the identity map, for example, then this will give you the free loop space of your manifold. Yeah. So this is, if two manifolds are homotopy equivalent, then their twisted free loop spaces are also homotopy equivalent.
Okay, thank you.
Mm-hmm. Okay. So let me say what happens equivariantly. Oh, sorry, go ahead.
Sorry, yeah. Are there any sort of, are there known counterexamples for dimension 2?
Yeah. So there's some example with the surface of genus 2, where you have maps in which these this invariant agrees, but you can't remove the fixed points, and it has something to do with passing to the universal cover and doing something there, sort of. Yeah, but there are counterexamples in dimension 2.
Thanks.
Mm-hmm. So what is the name of the paper for the Klein-Williams theorem? So this is called, I think it's called homotopical intersection theory. So this is homotopical intersection theory 1. That's the non-equivariant one. And then the equivariant one is homotopical intersection theory 2.
Thank you.
Thanks, Kate. So Kate put the link to it in the chat. Okay. So here's what happens equivariantly. So there's going to be a similar kind of theorem, some invariant, and it's going to be a complete invariant under some conditions. So let me write down an assumption, because it is a bit longer than the assumption that M has dimension greater than or equal to 3. So I'm going to want to be able to refer to it rather briefly. So an assumption that we can make about a G manifold is that M is a, let's see, compact G manifold, such that, first of all, if some subgroup H appears as an isotropic group, in M, then the dimension of the submanifold MH, so things fixed by H, is at least 3. So this is just like, I guess, a straightforward equivariant generalization of the assumption in the non-equivariant theorem. We just want all of the fixed submanifolds to have dimension at least 3. Okay, because in particular, if you can remove fixed points from M equivariantly, then you can remove the fixed points from all of those fixed submanifolds. So they all better have dimension greater than or equal to 3 for the same kind of theorem to work. All right, and if H and K are two different strictly contained subgroups that appear as isotropic groups in M, then the dimension of MH is at least the dimension of MK plus 2. All right, so this is kind of to make sure that certain things are simply connected when you pass from one submanifold to the next bigger one. Okay, so those are going to be the assumptions. So then the theorem, which is again due to Klang and Williams, at least in this formulation, is that for F from M to M, where M is a G manifold, so let's say equivariant, there is an invariant let's denote it chi GF because it's equivariant invariant now, and it lives in the 0th pi G of the suspension spectrum of LF of M. Such that, well, the first part is just exactly analogous. So if F is equivariantly homotopic to a map without fixed points, then chi GF is 0. And then the converse is that if this invariant chi GF is 0 and the manifold M satisfies the assumption star above, then F is equivariantly homotopic. To a map without fixed points. All right, so that's the equivariant theorem, and indeed, like after some mild conditions, then you know that this invariant is a complete invariant for telling you when you can remove the fixed points from the map. Okay. Okay, so yeah, maybe I'll pause again for a few seconds just to see if there are questions about this before moving on to the sort of saying what we think happens isovariantly.
In general, can chi GF be interpreted as a count and a generic representative of the equivariant homotopy class of F? Do you want to count fixed points?
Yeah, for sure. Yeah, so generally this chi GF is counting for you fixed points, but it's also counting like which orbit these fixed points appear in, for sure. Yeah. So, so one thing that's really nice about the Klein-Williams stuff is that you don't have to really talk about genericity at all. So a lot of things about fixed points or intersections or things like that, you have to say, okay, well, let's homotope things so that they're transverse to each other, and then count the intersections or count the fixed points then. So over here, like, equivariant transversality is extremely bad. Yeah, you don't really want to think about it. And so they really just don't have to deal with it at all. It's kind of this, one of my favorite tricks of replacing transversality assumptions by Poincare duality. So it's a great thing. So yes, M upper H, those are the points that are fixed. Yeah, so MH, those are all the X's that are fixed by every element of H. Yep. Okay. So, right. So let me say what happens, or what hopefully happens isovariantly. So maybe one thing to note, well, an isovariant map is in particular equivariant, and so you can apply this equivariant invariant to it. And so what we think happens in this case is that if we have an isovariant map, and M satisfies this assumption star, and this chi-G of F is 0, then F is isovariantly homotopic as well to a map without fixed points. Okay, so this is kind of telling us that under these same assumptions that happen in the equivariant case, equivariantly being able to remove fixed points of a map also means that you can isovariantly remove fixed points of a map in the case of manifolds. So this is not true if it's not a manifold. So one of the reasons why we think this is true is because it's true when your group is CP, so the cyclic group of prime order. So this is true for a cyclic group of prime order. And so then the hope is that we can leverage that, do some kind of inductive process to show that it's true for every finite group. So that's kind of the idea here. All right, so I should say kind of maybe what we're hoping to do. So the equivariant case is proven by induction. So it has some sort of induction. On the group G or subgroups of G or whatever it is that you want to call it. And so the hope is to build on this inductive approach to prove the isovariant theorem. So to prove the conjecture. So let me say a little bit about how this inductive approach goes. So what we do is we say that parentheses H is less than parentheses K if H is subconjugate to K. Right, so this is like if there's some subgroup conjugate to H, which is a subgroup of K. And so what Klein and Williams do is they extend this to a total order on the subgroups of G. Or maybe I should say the subgroups of G that appear as isotropy in M. Okay, so let's call the biggest group that appears H0, the next one H1, and so on up to Hn. And so maybe H0 is G, maybe Hn is E. Maybe they're not, maybe those don't appear as isotropic groups. But anyway, then you can define sort of a way of building up your manifolds inductively from the fixed submanifolds for all these groups. So Mk is all of the MHIs for I less than or equal to K. And so maybe I'll just say MHI, that's points fixed by subgroup conjugate to HI. So for example, if your group is maybe C6, cyclic group of order 6, then maybe you would have C6, which contains C3, which doesn't contain C2, but we're extending the order. So we can pick which one of C2 and C3 is bigger in our world, which contains the trivial group. And so then you're building this submanifold by, well, first maybe you have this orange thing, and then maybe you have, so this is MC6, and then maybe you're adding in MC3, and then maybe you're adding in MC2. All right, let me write this in a different color because the yellow isn't showing up well. And then you're adding in the rest. So then the blue is the free stuff. So this is ME. So this is kind of building up the manifold inductively, and that's the kind of things that we'll want to induct on to remove the fixed points at every stage. So there's also kind of a local version of that chi-G invariant. So if you're assuming F has no fixed points on Mk minus 1, then there's an invariant chi-Gk of F, which measures whether you can extend that. So whether you can remove fixed points on the slightly bigger thing, Mk, and you want to do this while not changing all of the steps that you did before. So you're leaving F on Mk minus 1 fixed. So this invariant is kind of the key of the induction. If this invariant is 0, then you can extend however you remove those fixed points before, you can extend that up to the next subgroup. All right. So let me say a little something about, so sort of extending from mk minus 1 to mk relies on, well, it relies on various things like those, that gap in dimensions between the fixed stuff as well. But some sort of like very basic things that it relies on that I want to emphasize are these. So mk minus 1 to mk is an equivariant cofibration. So you get mk from mk minus 1 by adding equivariant cells. And another one is that all G spaces are fibrant. So one sort of like, I guess maybe more basic homotopy theoretic things that it relies on, that if you add another one of those fixed manifolds, you get an equivariant cofibration, and all G spaces are fibrant. This is to do some kind of homotopy extension thing. Like you have a homotopy, you want to extend the homotopy. And so that's kind of things that are implicitly going into this proof every time that you do the induction. So we want this for homotopy extension. Okay. So let me say kind of what happens isovariantly, what we want to sort of get from this isovariantly. So here's how we want the inductive approach to work isovariantly. So one is, well, let's take that very first or 0th local invariant. So if that's 0, then we can isovariantly remove the fixed points on MH0. So this MH0, that's usually MG. That's usually the things fixed by the entire group. And this is because we can equivariantly remove them. So this is saying, well, for the largest subgroup that appears as an isotropic group, so for example, G itself, if you can equivariantly remove fixed points on MG, you can isovariantly remove fixed points on MG. So that's kind of the basis of the induction. And then the second part is to extend, so the induction step is to extend this isovariantly from the same mk minus 1 to mk. All right, well, in order to do that, we need these two kinds of homotopy theoretic things to happen. So we need some kind of model structure on isovariant spaces such that, first of all, mk minus 1 to, let's say, mk, or even m itself would probably be enough, is a cofibration. So you can get from mk minus 1 to the next thing by adding isovariant cells. And then second part, you want your manifold M to be fibrant. So that's kind of, if you want to carry out this induction, then you want to make sure that you have a good homotopy extension property at every step. So that's what these assumptions are doing. And so the first candidate for a model structure on isovariant spaces is the elementary model structure. And this is something that Sarah developed and put on the archive in 2019. And so this is a really nice model structure in the sense that, for example, there is an Elmendorf's theorem for it. So in this model structure, you can explicitly build an equivalence with some kind of pre-sheaf category. So I'm not going to tell you what this model structure is right now because we're running out of time, but I will tell you that there's a problem with it, and that's that not all manifolds are cofibrant. So things like part A here, where you want this mk minus 1, including into m, to be a cofibration, that's just not necessarily going to be true. So for example, the disk with rotation action. Is not cofibrant in this model structure. So that's going to be a pretty big problem. That's like a pretty elementary kind of manifold. Okay, so the second candidate is the geometric model structure. So this is one that we've been kind of working on for this kind of fixed point problem. And one thing we have for it is that manifolds are cofibrant, and that this k minus 1 thing, including into m, is a cofibration. And then what we don't know is whether manifolds are fibrant. And this is so far turning out to be pretty tricky. So this is the sort of big question that we're left with somehow, which is, are manifolds fibrant in this model structure? So I should say this geometric model structure is Quillen equivalent to the elementary model structure. So it's describing the same homotopy theory of isovariant spaces, but we're hoping for it to have better fibrations and cofibrations to help us solve this fixed point problem. And so if manifolds are fibrant, then the conjecture is true. Then we can run through this entire induction and show that the equivariant invariant, so if we can equivariantly remove fixed points, then you can isovariantly remove fixed points. And this is for manifolds satisfying this assumption star that we said about all of the fixed submanifolds having dimension at least 3, and them having codimension at least 2 in each other. So under these assumptions, if you can equivariantly remove the fixed points of a map, you can isovariantly remove the fixed points of a map. Yes, so there's a good question in the chat. What do you mean by fibrant if you don't have a terminal object? Or is this the problem? So this is not the problem so far. So what I mean by fibrant is that if you have a cofibration, sort of maybe a cyclic cofibration, then you can lift it. So that's what we mean by fibrant. That's all. Yeah, so maybe in the last minute or less, I'll say, well, this is, so maybe some other things that we're sort of thinking of as things that would interest us to know in the future. What happens when you're talking about things that aren't manifolds? So this conjecture can only be true for manifolds. We already have counterexamples where you have different invariants coming up for non-manifolds that don't show up in the equivariant case. So what happens when it's not manifolds? And also the Klein-Williams proofs, they rely a lot on stable homotopy theory and on equivariant stable homotopy theory. So we're really kind of interested in knowing what is isovariant stable homotopy theory. Like, it's got to be at least somewhat different from equivariant stable homotopy theory, but we don't know what it is. All right, so I'll stop here.
Thank you. Let's all thank Inbar, and then we can ask some questions.